As far as precise definitions involving limits, this should be the last one, and I want to define what it means for the limit as x goes to infinity of f of x also equals infinity. So this is a limit at infinity where the limit is infinite. This happens, or let me just say this means that for any m greater than 0, there is a real number n such that if x is greater than n, then f of x, or y, is greater than m. So let me pick one. I'm pretty sure I proved this before, but let me prove this one here. Prove that the limit as x goes to infinity, x to the p over q equals infinity, where both p and q are positive numbers and p and q are integers, positive numbers and integers. So before I do that, I'll have to do a couple of things just to show you something. My first thing I want to show is that x to the 1 over q is increasing. For positive x values. What does that mean? That means that if x1 is less than x2, then f of x1 is less than f of x2. Or you can see, let me draw sort of a really silly little picture to indicate this here. All I'm saying is the function's increasing is if I pick a number, x1, and another bigger number, x2, then when you look at the graph, the y value associated with x1 and the y value associated with x2 maintain the same inequality. That means f of x1 is less than f of x2. So you can see when x1 is less than x2, the graph, this type of graph, indicates that y1 is less than y2. So I want to do this for x to the 1 over q. And everything's positive, so no big deal. So let me see if I can make that happen. Suppose, let's just start out with this. Let x1 be less than x2. So x2 minus x1 is greater than 0. Now, if you'll recall, there's a really freaky way to factor this that I did in one of the earlier sections. And I can take and write x2 minus x1 equal to x2 to the 1 over q minus x1 to the 1 over q times x2 to the q minus 1 over q plus x2 to the q minus 2 over q times x1 to the 1 over q plus dot, dot, dot. Remember this piece here, after the minus part, this piece here is called the conjugate. I gotta write it all out because I really don't need a lot of it. I need, just so you can see what I'm doing. And really all I need to know about this is the fact that this conjugate is a positive number. That's all you really need to know about this, because this x2 minus x1 I already know is greater than or equal to 0. So if I set this greater than 0, I can simply divide both sides by that conjugate. And then I can add x1 to the 1 over q to both sides. So it preserves that order. The same is true with a number to the p. If I say x to the p is increasing, then what I'll do, here p is a positive integer. What I'll do in this case, I'll do x1 minus, no, I'll keep the order of x2 minus x1 times x2 to the p minus 1 plus x2 to the p minus 2, x1 to the p plus dot 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 plus x2, actually let me fix that there, so I get x2 to the 1 times x1 to the p minus 2 plus x1 to the p minus 1. All that stuff equals x2 to the p minus x1 to the p. So if x2 was greater than x1, then this piece right here is positive. All of the numbers involved in here are positive. So I have a positive times a positive. That tells me that this thing is greater than 0. So I have that those two things are increasing functions. Now, let's prove this limit. The limit, as x goes to infinity, x to the p over q equals infinity if p, q are positive and p, q are integers. And so, like anything else, let's scroll back up here for a minute. On m, a value will be given, any m greater than 0, and we'll have to try to figure out the n that'll make this thing work. So let me scroll down. So let's go proof. And like before, let m greater than 0 be given. Almost like let epsilon be given. There's a similarity to all these things. Now, what I need to get to eventually, I need to show that x, well, I need to find an n where x to the p over q is greater than m. Well, this is nice, because then if I take both sides to the q over p, this is what I was just talking about here, except you'll rearrange the p and the q, because taking something to the q over p is an increasing function. It maintains the inequality. Well, this right here will work as my n. So, let me just circle this stuff because it's not part of the proof. I just use it as a thing. A little worksheet there. Perhaps I should have done it off to the right, but nonetheless. So if m greater than 0 is given, let n equal m to the q over p. Then x, well, x greater than n means that x to the p over q is greater than n to the p over q. X to the p over q is greater than, and n equals m to the q over p. And of course, all those exponents cancel, and you get this equals m. And that's all there is to that one.